Hello, everyone. So today we're going to continue our conversation on molecular partition functions by focusing a little bit more on our last three degrees of motion, starting with our good old friend, molecular rotations. So by applying quantum mechanics, it's possible to get energy levels for the rotations of a linear molecule. The energy levels are going to be based on beta, again, our good old friend K, 1 over KT. The Planck's constant, the speed of light actually shows up here, partially because our next variable here of beta is going to correspond to the distinct energies of rotations in units of inverse wave numbers, and HC essentially helps convert the units back into joules. And then we have this mysterious variable J. So J here is essentially referring to the rotational quantum number. And really a good way to think about it is it's going to correspond to the speed of rotation. So if I have a J of 0, it essentially means I've got no rotational energy. Where as soon as I have a J of 1, now I've picked up speed a bit, J of 2, 3, and so on. As J goes up, the speed of rotation goes up, and you can figure out the energy of that corresponding speed by knowing your B, your rotational constant, this B value. So there's a lot that actually goes into trying to calculate B, and we'll talk more about that in PChem too. But all we need to really know right now is that the rotational constant is going to be defined by the molecule of interest. And in general, a good way to think about it is you're going to tend to have larger values for heavier molecules, which is going to tend to result in much tighter, closely packed energy levels. And so one of the things that we specifically have to worry about with rotational energies that we didn't have to with translational energies is the fact that there is a degeneracy factor when talking about rotations. Because it turns out that as J increases and you have faster and faster rotations, well, it turns out the directions of those rotations also increase because it's now more possible to get rotations in, say, not just the x direction, but x, y, y, z, essentially kind of cutting corners around this idea of rotating about a sphere. So as the energy levels go up, we're going to pack the energy levels tighter and tighter. So when we pair together this feature of degeneracy plus energy level, what we essentially end up, what ends up resulting is a partition function where I'm going to be summing over all of my various J values, and this term is going to keep getting bigger with higher and higher J values, whereas this term is going to get smaller and this exponential term gets smaller and smaller because as J gets bigger, I've got a more negative exponent, which drives the value closer and closer to 0. Well, this one's going to increase faster. Now, part of the trick is that this increases linearly, while this term decreases exponentially. However, one of the interesting things about when you try and combine essentially algebraic and exponential factors is it almost always generates some sort of happy zone in the middle. Because at the beginning, this essentially algebraic increase of degeneracy drives the production of larger and larger values for the partition function. However, once you reach this kind of critical value, there's no overcoming an exponential in the long run. You can beat it in the short game, but you'll never beat it in the long range. And so as a result, it turns out the most commonly occupied states are going to be here in the middle. And those are going to be those of intermediate energy. They're common enough that they'll occur fairly frequently, but they're low enough energy that they're accessible. And it's trying to balance these two. So again, degeneracy is going to tend to favor high J's, while energy tends to favor low, and it's trying to balance them on a razor's edge right here. Now, one of the things that we can actually make use of is in practice, most of the energy levels for the partition function are essentially tightly enough tightly enough packed, it's possible to turn this sum into an integral. And when you actually go ahead and integrate the system, again, just like translational forms, it's going to give us uh, a well-known form of an integral solution, which in this case abbreviates to uh, Boltzmann constant times temperature over hc times our rotational constant. However, it would be possible to rephrase this expression in terms of hcb beta, because again, beta is 1 over kt. And again, you'll occasionally frequently see this rotational constant put in terms of energy instead of wave numbers, at which point you get rid of the tilde, and it could just be 1 over beta b. However, we're going to tend to focus on this more common notation that you're more commonly going to encounter, especially because one of the useful things is that it's possible to actually derive the rotational constant from experimental findings, and that's typically presented in wave numbers. So, but more importantly, it's worth noting that right here, our only variable really is going to be t, because speed of light, Planck's, and Boltzmann are all constants. And it turns out this b is going to be dependent upon the nature of the molecule of interest. So most of the time, you're frequently going to find the partition function essentially collapse down into 2 single variables: temperature, which is going to be described by the system that you're present in, and this theta value, which is referred to as the characteristic rotational temperature. And this is, again, going to mostly be dominated by the rotational constant, more or less just changed for units of Kelvin. So this essentially is going to be a way of representing the rotational structure of the molecule of interest. And again, is mostly going to, again, if you remember the structure B, in large part be driven by the mass of the system. And what's going to tend to occur is that in order for our partition function to hold, just like in translational motion, our energy levels need to actually be fairly close together. And this is going to only tend to happen when our temperature is going to be much greater than our characteristic rotational temperature. So otherwise, our approximation that we can treat the sum of rotational levels as a constant integral breaks down a little bit, and we'll get increasing levels of error. However, this is actually a surprisingly good approximation because, again, heavier molecules tend to have lower characteristic rotational temperatures. And it turns out that the lightest, smallest molecule you're going to end up with, H2, has a characteristic rotational temperature of about 90 degrees Kelvin. And it turns out that most rotational temperatures are much below that. So as long as you're not working in ultra-cool systems, or maybe even something as cool as, say, liquid nitrogen, it turns out that this is actually a fairly good approximation. And it's fairly safe to use the rotational temperature while trying to calculate the rotational partition function. However, there is an additional approximation that we occasionally have to make, which is that some molecules have additional symmetry constraints. And you need to essentially account for them by trying to essentially modify our partition function. So one of the most notable things is that we have to account for essentially symmetry, which is essentially if I have a highly symmetric molecule where multiple of our rotations look almost identical, this is going to give us identical or degenerate energy levels, which is going to greatly increase the partition function because we essentially have more possible energy states. And so for a symmetric linear molecule like hydrogen or CO2, what ends up happening is that the symmetry value has 2, because essentially with no way to differentiate the ends of our molecules, because I have a hydrogen on either end of H2 and an oxygen on either end of CO2, I I've essentially doubled the effective degenerate energy levels. So we're going to have a much larger characteristic rotational constant. However, if I have heteronuclear uh, molecules, so things like CO or HCN, so ones where it's very clear to see which end is which, then we get to use the previous version of just temperature over characteristic temperature. And using this, we can go ahead and back out our rotational partition functions, which will help us determine many observable features, which we'll bring up later. However, we still have two more partition functions to deal with. The next up is vibrational partition functions. So it's important to remember that every molecule has multiple bond vibrations. Many of these typically absorb in the infrared, and when you're using IR spectroscopy, this is really what you're looking for, is these bond vibrations. For example, CO2 has a characteristic bond vibration of carbon with the two CO bonds at around 1,333 inverse centimeters. However, the problem is there isn't just one vibration per molecule. So if I've got a linear molecule, I'm going to have 3n minus 5 vibrations, where n is the number of atoms in a molecule. So a small molecule, like a diatomic molecule, where I only have 2 atoms, this would be 2 times 6 minus 1. I only have 1 vibration, which makes sense because all my other movement is caught up in rotations and translations. In fact, 3 translational degrees of freedom and 2 rotational, leaving me only 1 vibration. However, with CO2, when I've got 3 atoms, I've got 3 times 3, so 9 minus 5. I've got 4 different vibrations. Those occurring in between carbon in each of the 2 oxygen atoms, as well as essentially bends in and out of the plane. However, when you have nonlinear molecules, you essentially gain an extra rotation and essentially lose that at the cost of a vibration. So if you have a nonlinear molecule, you're going to have 3n minus 6 vibrations. So essentially 1 fewer vibration than for a linear molecule. So one of the important things to note is that each of these vibrations is characterized by a characteristic frequency V. So this characteristic frequency is usually what we're measuring with IR spectroscopy. Because if I go ahead and if a molecule absorbs a photon in the IR range, what I've essentially done is I've excited from one energy level to the next. So not too surprisingly, the energy separation can essentially be given by Planck's constant times the speed of light times v, which is again the vibrational frequency in inverse centimeters, as you see here. And Planck's constant times the speed of light essentially just gives me unit correction. However, one of the important things is I also have to build in the fact of the energy level. If I'm in the 0th energy level, I'm in the ground state and it works fine. The first energy level has a value of HCV, and the second would have 2HCV, and so on and so forth. So this is actually quite conducive to trying to build up a partition function. However, one of the things that is worth noting is that because we have uniform separation in between the vibrational levels, it's actually possible to kind of simplify our vibrational partition function instead of a simple sum as to the form of 1 minus E negative beta times the separation value of our energy levels, using again another trick of linear expansions. So this is actually kind of a quite nice and useful feature because we got rid of that traditional sum that we're always having to deal with when working with partition functions, which is again very useful. However, one of the other useful parts of this is that if I've got essentially very low frequencies or high temps, thus low beta values, the system actually breaks down uh, a little bit more, and the partition function can actually simplify to kt over h times a Planck's constant times the speed of light times, again, my characteristic vibrational frequency. So again, by simply knowing my vibrational frequency, either if I'm dealing with tightly packed energy levels as demonstrated by low frequencies, so low separation, or high temps where maybe we're able to overcome those low frequencies, you're able to get to the actual partition function. But even if you can't make this approximation, it's still fairly easy to try and solve the partition function for a vibrational system. And it's actually worth noting that when you do quantum mechanical calculations and you do a vibrational calculation, really what you're trying to do is determine these V values so you can solve for the vibrational partition function, which is actually, as we'll see later, plays a crucial role in trying to determine enthalpies, entropies, and free energies. However, one of the important things to note is that all of this work goes into just solving the partition function for only a single vibrational frequency. However, turns out we have a lot of vibrational frequencies. However, we can use the same separability we did earlier, and you can determine the total vibrational partition function simply by using the product of each of the individual vibrational partition functions. So if you have 5 vibrations, you'll have to calculate 5 separate vibrational partition functions to generate a net product vibrational partition function. So a little inconvenient, but fairly useful, as long as you're able to get those vibrations, you can back out the partition function and on to energy. However, that leaves us with one last partition function, the electronic partition function. This one actually turns out to be almost the easiest of the set, because it turns out that when you're dealing with electronic energy levels, as found in nitrogen, what we tend to notice is that most of our energy levels are actually greatly separated. And because these energy separations are actually fairly large, you're almost always going to find a molecule in the electronic ground state. And as a result, for most systems, the partition function is 1, because there is no occupation of the excited state. It is worth noting that there is several systems at which point this breaks down, and they are often neglected. So it's important to know that they're out there. So what you're going to be looking for is systems where the energy levels are very tightly packed around this HOMO-LUMO gap. As my highest occupied and my lowest unoccupied get closer and closer, you're going to see some occupation of that excited level. However, this is typically only going to be very common for molecules that involve metals, because metals with so many more orbitals tend to more closely pack their electronic energy levels. So as long as you're not dealing with a metal-containing species, whether it's an organometallic or a metal surface, you can generally ignore the electronic partition function, though it's important to realize that it might be out there. So we just spent all this time talking about partition functions. Next time, we're going to try and learn how to use them, and how can you turn a partition function into the energy of the system. Until then, take care.